Hello and welcome back to chapter 3, section 3. We're going to do properties of functions today. We're looking at college algebra, and our objectives today we're going to identify even and odd functions from a graph and an equation, determine whether a function is increasing or decreasing, or is it constant. We're going to locate max and mins today and talk about local max and local mins and absolute max and absolute mins. Take a look at doing some of this on graphing utility, and then find the average rate of change of a function. Those are the ideas that we want to get accomplished today. Let's start off by just doing some basic graphs. Let's go ahead and make a graph of y equals x and y equals x squared. We're going to use a table of values to do this. Then we're also going to describe the symmetry. So if I take a look at this first item that we have here, we have y equals x. That's our first item. So we have our t-chart here. We have our x values on the left, y equals x on the right. And this is the identity function. So when we take a look at y equals x, whatever value for x I choose, and typically, again, we're going to choose kind of our standard questions, -2, -1, 0, 1, and 2. When x is -2, y is the same value. So y has got to be -2 when x is -1. Y equals the same value, and likewise with all of these. And then if we go ahead and do a quick graph of that, let's see, at -2, we're -2, -1, we're -1, 0, 0, 1, 1, 2, 2, and it looks like we end up with a nice little line there. When we take a look at y equals x squared, let's go ahead and graph that one then. When we take a look at y equals x squared, let's see, I've got, and when x is -2, what I end up with is the square of -2, and that ends up being +4. Then I'll end up with the square of -1. So -1 times -1 is +1. 0 squared is 0. 1 squared again is 1, and 2 squared is 4. So we've graphed these items before. We'll go ahead and put these back in here. So -2 are 4. -1 is 1. 0, 0, 1, 1, 2, 4. And on this one, we end up with a nice little U shape, and we call that a parabola. So as we take a look at this, a couple of things to pay attention to. Our initial objectives, what we want to do is identify even and odd functions from graphs and also from equations. Well, how do we identify evens and odds? What we can do then is down here at the bottom, look at the powers of each of the functions. Okay? So if I take a look at y equals x, that's really y equals x to the first. This power here, 1, is that an even or an odd number? Well, that is an odd number. And likewise, if we take a look at y equals x squared, if we just take a look at the 2 is an even number. So as we take a look at those, part of what's going to be taking place here is taking a look at the exponents on our function and determining whether it's even or odd. That's part of the idea. As we take a look a little bit closer at the graph, if I take a look at the line y equals x, one of the things we take a look at is some symmetry. And we say, okay, what does symmetry look like in these things? And can we identify some other items that kind of come along? So as I take a look at this first one, as far as y equals x, it's not symmetrical about the y-axis, so I can't fold it right and left. I can't fold it up and down over the x-axis. What we can do is we can fold it over the origin. So I can say, what if I take this point 1, 1 here, if I would reflect it over the y-axis and then also reflect it over the x-axis, we end up with another point. And so we say this is symmetrical over the origin. Likewise, another thing that we can take a look at is if I have a point xy on my graph. So for instance, we had 1, -1. Let me move this just a little bit. So I had 1, -1. What's the symmetrical point to 1, -1? What was -1, -1? So it's -1, -1. So what happened then, as we take a look at this, is I ended up, if xy was on the graph, was x, excuse me, made a minor mistake there. It was the point 1, 1, not 1, -1. So if I take a look at 1, 1, reflect it over, and then reflect it again, we end up at -1, -1. So what ends up happening is I end up with -x, -y. So both my x coordinates change. If we take a look at y equals x squared, So if we take a look at that one, this is going to be symmetrical over the y-axis. We can see that one fairly quickly. I can fold it from right to left over this line here, and so these points just reflect and they are symmetrical to each other. So it's going to be symmetrical over the y-axis. And let's see, if I have the point 1, 1, what happened to it? It became the point negative 1, 1. So any xy pair that I ended up with being the opposite of x and then the corresponding y value. And as we take a look at these are some interesting items as far as what is happening when I plug in negative x. So if I take the opposite of the x value, what happens? So overall, when I'm symmetrical over the origin with an odd function, let's take a look at the definitions here. Definition of an even function, we'll do even first since that's what's listed here. A function is even if for every number x in its domain, the number negative x is also in the domain, and f of negative x equals f of x. So when we take a look at that, if here's an x value, okay, so let me do it this way. So if here's going to be some x value, there's going to be negative x. This will be symmetrical if f of x, okay, if f of x is going to be the same height as f of negative x. So if those two match, so they're going to be symmetrical over the y-axis, then we have an even function. If we take a look back up here in our function for x squared, okay, what we're saying is if we are an even function, what we're saying is f of negative x equals f of positive x. Well, let's see back over here. If I plug negative 2 in for x, I get a y value. F of negative 2 is 4. And likewise, if I do f of 2, I also get 4. So whether I'm using 2 or negative 2, so whether I'm using x or negative x, we end up with the same height, so the same y value. If the y values are the same, whether we plug in a positive x value or its corresponding negative, then we are an even function. If we take a look at odd functions, what happens then? A function f is odd if for every number x in its domain, the number negative x is also in the domain, and f of negative x equals the negative of f of x. Okay? And so in this case, we are symmetrical over the origin, which is what we're doing down here as far as the theorems. A function is even if and only if its graph is symmetric with respect to the y-axis, and a function is odd if and only if it's symmetric with respect to the origin. As we take a look back up here on our odd function, okay, we said what happens then, so if I plug in negative x, what I end up with is the negative of y. Another way to write the y value is f of x. So if I take f of negative x, oops, let me do it this way. If I take negative x as my x coordinate, another way I can write the y coordinate is f of x. So this becomes negative f of x. That's the notation that's taking place there. So if 1, 1 is on the graph, okay, which it is, so 1, 1 is on the graph, then we're saying negative 1 is going to end up being the negative of the original y value, which it is. Okay? So my y value switches signs down here also. So overall, when we take a look at even and odd functions, we can take a look at them graphically. Where is it symmetrical? We can also take a look at it algebraically. Algebraically, what we're interested in is what happens to negative x. F of negative x in the even function, the negative cancels itself out. Think about the square of a negative. So the square of a negative, a negative times a negative is positive, the negative goes away. If I have an odd function, so a negative to an odd power, 1 negative is still negative. 3 negatives is still negative because I'd end up with negative times negative times negative, which overall is negative. And if I do even functions, if I have a negative and a negative, that ends up being a positive. Okay? And so that pattern takes place all the time when we think about our functions here. So let's take a look at some examples. Just based off a graph, can we identify is a function even or odd, or is it neither one of those? We can have functions that are not even and that are not odd. Since we have a number that's not even or not odd, so 0 is neither even nor odd. No, 0 is positive nor negative. Well, got ahead of myself on that one. So scratch that, ignore that comment there. We'll stick back with the script here. Identifying even and odd functions from the graph. We're identifying then if it is going to end up being an even function, it's got to be symmetrical about the y-axis. If it's an odd function, it's got to be symmetrical about the origin. So if we take a look at example A, and we see, do we have any symmetry here? I can see that we are symmetrical about the y-axis. Take a point on the right side, I can fold it over, it's on the left. If I'm on the left, I can fold or make it on the right. So since this is symmetrical about the y-axis, this function is an even function. As we take a look at letter B, if I take a look at the y-axis here, if I take a look at this point here, if I fold it over to the right side, it should be here. Well, there's not a point there. So this is not symmetrical about the y-axis. Might take a look and see if it's symmetrical about the origin. So if I take a point here, symmetrical about the origin, then I should be able to flip it over the y-axis, then also flip it over the x-axis. So if it was symmetrical over the origin, I should have a point down here, which I do not. So since it's not symmetrical over the y-axis, and it's not symmetrical over the origin, then this graph here is neither even or odd. It's neither one of those. Take a look at example C here. This is going to be an example of something that is going to be an odd function. You know, if you've been around school very long, you notice that we end up with examples that are and examples that are not. We've already done an example that is even, an example that's not, so we probably end up with an example that's odd. Typical way to fashion this. Let's double check this. So I've got a point here. If I reflect it over the y-axis, it's over here. If I reflect the same distance over the x-axis, it's down there. So I do end up with that matching, and so I end up with an odd function because it is symmetrical about the origin. All right, so what if we take a look now at just equations? So algebraically, how do we determine if an equation is going to end up being symmetrical with respect to the y-axis, symmetrical with respect to the origin, or is it neither? So basically, is it an even function, an odd function, or neither? And then once we have these, I've got a Desmos loaded up here. We'll take a look at Desmos also. So our idea here is, what do we do with f of negative x? So that's going to be a key piece. So when we took a look back at our definitions previously, what do we do with negative x? If our negative in the x, if it goes away and we end up with just positive f of x, then we're even. If we have a negative, so f of negative x for our odd function, it comes outside and goes in front of the function. So if that's the case, then we have an odd function. So how do we show this? All right, so let's take a look at f of negative x. What we're going to do is we're going to plug in negative x for all the x's and then see what happens. So instead of x squared minus 5, I'm going to have the negative of x, that thing squared, minus 5. So the square of negative x is negative x times negative x is x squared. Minus 5 didn't change. So I end up with x squared minus 5. But wait a minute, x squared minus 5 is the same as f of x. So what we see here then is f of negative x equals f of x. So since the negative gets swallowed up, when does a negative get swallowed up? Anytime we take a negative to an even power, it'll get swallowed up and turn positive. So this particular function then is going to end up being an even function. If we take a look at the graph real quick here, f of x is x squared minus 5. Let me zoom this back in here. So there's the graph of x squared minus 5. If I do f of negative x, it goes right over top of it. It is the identical item. Nothing changes. If I was looking at negative f of x, then I would have had a different shape. But so negative f of x is not the one that we have. We have f of negative x, which is just the same as f of x. So we end up with an even function. taking a look at letter B. We've got g of x equals x cubed minus 1. So what happens then when we plug in negative x? That's our question. What happens with the negative? So I plug in negative x for x. So I got the negative of x, that quantity cubed, then minus 1. So negative cubed, negative to an odd power, so it's going to be negative. So I get negative of x cubed minus 1. So that is what g of negative x is. Is that the same as g of x? Well, it's not quite the same as g of x because g of x just has x cubed minus 1. So that's not the same as g of x. So that means it's not an even function. What then would have been the negative of g of x? So here's a question. The negative of g of x would have been the negative of x cubed minus 1, which would have been negative x cubed plus 1. As we take a look at that, what we're asking then, are these two items the same? If those two are the same, if g of negative x is the same as the negative of g of x, so the negative sign moves from inside to outside our function, then we would say that we had an even, or excuse me, we would say we had an odd function. But these are not the same. So g of negative x is not the same as the negative of g of x. So it's not an even function. It's not an odd function. So this is neither. Letter B is in neither. So as we take a look at that, let's see. I've got x cubed minus 1. That would be the shape. And as we take a look at that shape, we can identify that it doesn't fold right and left, and it doesn't fold right, left, and then up, down either, at least not across the origin. So here's g of negative x, not quite the same, and the negative of g of x. Okay, so we don't have that symmetry, so this one ends up being a neither. Take a look at letter C. Let's see, letter C. Overall, that one was h of x equals 5x cubed minus x. Again, we're asking what happens when I substitute negative x in for x. So, doing my substitutions. And again, one of the things I like to do when I do these substitutions is I put these parentheses in here because that way I'm less likely, not say completely eliminate it, but less likely to make a mistake with my signs. Okay? So let's see here, h of negative x, let's see, negative of x cubed, excuse me, or negative x cubed rather, there's a negative times a negative, which is positive, times another negative, which is negative, so with negative 5x cubed, double negative again, so I end up with negative 5x cubed plus x. So is that the same as what I started with? No, it's not the same as what I started with. So that's not the same as h of x. So it's not going to be an even function. Is it the same, however, as the negative? Is that same as the negative 5x cubed minus x? Okay? If that's the same, then we match up. And what we see here is that is going to match because that would be negative 5x cubed if I distribute that through, then plus x. So this piece here, that was the negative of h of x. So h of negative x is the same as negative of h of x. So this is an odd function. Okay. So what we're comparing then is h of negative x, which I ended up with is that piece, ended up being just the opposite of what the original was, and in that case then we end up with the odd function. If we take a look at that one, let's do this graphically. So here's this particular graph, okay? And what happens with h of negative x? Okay? Is h of negative x the same as the negative of h of x? And we see it is. So if I go ahead and toggle it back and forth, that ends up being the exact same graph. So that indicates that that is an odd function. Now, one thing to note here as we go through, when we had our even function, look at what all the exponents were. I had a power of 2. This technically could be 5x to the 0. Anything is 0 power is 1, so we don't have to write that. So when all the exponents were even, I end up with an even function. Over here, I had x cubed minus 1x to the 0. I have an even function, excuse me, I have an odd number 3, and I have an even 0, so I have both evens and odds, ended up being neither. On letter C, I have an odd, and we ended up being odd. Okay, so one of the things we can look at is if every exponent is odd, then it's an odd function. If every exponent is even, certainly seems like that would be an even function. And that's a nice thing to be able to take a look at, and by inspection, we can identify, well, what is it going to end up as? Okay, one more example here. Didn't forget about it. Let's see, we've got f of x equals the absolute value of x. So this is letter D. So that's going to be the absolute value of x. So what if I take in here negative x? What happens? So if I plug in negative x, well, the absolute value of the negative still got to be positive. So that ends up being, in this case, that's still going to end up being the absolute value of x, which was the same as f of x. So my f of negative x is the same as f of x. And so then when that happens, if the even gets, excuse me, if the negative gets swallowed up, it is an even function. Now on this one, this is an odd case. I just talked about what are the exponents. This is a special function because this is the absolute value function. And what does the absolute value function look like? Well, glad you asked. We've got it over here. There's the absolute value function. So whenever we plug a number in, we want to take its positive value. Okay, so the absolute value of negative 2 is positive 2. Absolute value of positive 2 is still positive 2. So when I take the absolute, excuse me, f of negative x, they go right on top of each other. Okay, the negative f of x would have been a reflection over the x-axis, and that's not saying that what we had. And so in this case, we end up with an even function. Okay, so what we just took a look at then was identifying even odd functions algebraically, and the overall theme here was we plug in negative x. So we plugged in negative x to each of these, and then we identified how did the ending function match with the original function. Okay, were they the same? Were they not the same? So they were not the same down here. Over here, h of negative x ended up being the same as negative of h of x. And so those are the scenarios that we're referencing along the way as far as is it going to be even or is it going to be odd? So that was our first two objectives. Take a look at those. One of the other objectives that we have is identify whether a function is going to be increasing, decreasing, or constant. If we just think about the words, if something is increasing, that means it's going up. If something is decreasing, it means it's going down. If something's constant, it means it's not changing. So if I take a look just as an example of an increasing function, so let me choose just some first x point and some second x point. If I'm increasing, that means overall that I've got to keep going up. So from x1 to x2, f of x1 compared to f of x2, f of x1, if I'm increasing, f of x1 is lower, so it's got to be less than f of x2. If I take a look then at another point here, another graph, let's do x1, x2. If I'm going to be decreasing, here's my f of x1, here's my f of x2, and so x1 has to be bigger than, f of x1 rather, has to be bigger than f of x2 in order to get that decreasing look. And if I have a constant, so if I have an x1 and an x2, if I'm not changing, oh, got to be a horizontal line then. Here's my f of x1, here's my f of x2. They're going to end up being the same. Excuse me there. And so they're going to be equal to each other. And so we have increasing functions, increasing, decreasing, and we have constant. Now, more of the formal definition is what we had at the top here. function is increasing if on some interval. So if I take a look at any just small section of the graph, and any x and y's that I choose, the first x value on the left of the second x value, then the corresponding heights then have to fit certain requirements. Let's take a look at a graph here. Let's determine the values where the function is increasing, where it's decreasing, and where it is constant. So as we take a look at some graphs over here, where are we increasing? Let's do increasing first. So where are we starting to go upwards? So from -6 to -4, we're going down, but from -4 up here, looks like that piece is where we're increasing, and that's the only spot where we are increasing. So let's take a look at where we are increasing. So we're increasing between -4 and 0. Where are we then decreasing? Where are we moving downwards? Moving downwards over here. Looks like we're moving downwards over there also. So we're moving downwards between -6 and -4, my x values. And then combine that with another set, we're moving downwards between x value of 3 and an x value of 6. And where is the graph constant? Where did it not change? It didn't change in here between 0 and 3. So by taking a look at the graph, we can just identify visual inspection. Where's the graph going up? Where is it going down? Where is it holding steady? And that's just the idea then of when we are increasing, when we are decreasing, and when we are constant. So that was example 3 and objective 3. Figuring out when we're increasing, decreasing, constant. Not a whole lot to that particular concept. Let's take a look at concept number 4. What is our objective here? Objective number 4. Use a graph to locate local maxima and local minima values. So one of the things I've got set up here is, can we draw a graph with a local or relative maxima and another graph with a local or relative minima? Okay, and we have our definition underneath here. It says, let f be a function defined on some interval I, and let c be a number in I. Okay, so basically what we're saying is here, we've got this graph, and we have some open interval. So we're going from, here's an x1, here's an x2. An open interval means that we don't include those two. So there's going to be open dots. And what we want to do then is, if we want to go ahead and have a local maxima, okay? So as I go ahead and graph something here, maybe I do something like this. This height here corresponds to some value. So let's call this x value c. This height here then is f of c. On this particular interval, so the interval between x1 to x2, f of c is the high point. So if f of c is the high point, then that is going to end up being what we call the local maximum value. Okay? That means f of c, if I come back down here to the written definitions here, for a local maximum, it does have to be an open interval containing c. If f of c is greater than or equal to every other x on that interval, then we say that we have a local max. Likewise, if I go ahead and take any interval, let's go from an x1 to an x2. So here's my interval that we're referencing. And again, I can go ahead and do something like this. And let's call this point C again. And then we have this coordinates would be f of c. Notice f of c here is less than or equal to every other height on the graph. So if it's the smallest point in its interval, in its area, okay, so that's the idea here. We have to be a local minimum in an interval. So if we're in some interval and we are indeed the smallest value, then in that interval, then that point is the local minimum. If we are the highest point, then we are the local maximum. And one of the things we're looking at here is that this is really when our graph turns. So we were going upwards. So if I take a look at this graph on the left, I was going up, and then I started going down. Well, if I'm going up and then I turn back down, I have to have a high point there. If I'm going down and then I turn back up, then the lowest spot that I hit, that's my value I'm looking for. I have a local max or local min, where I end up turning on these items. Why we call these locals, okay, okay, why are we saying these are local values? Because we're restricted to some interval, restricted to some neighborhood, okay? So we're in some interval, or we're in some particular neighborhood, so to speak. So in this particular region, f of c is the smallest point. In this particular region, f of c is the largest point. What if, however, I did some other items along the way? Okay, if I did something like this, f of c is not the smallest height on the graph. Okay, if I'm looking over in through here, so f of c is not the smallest. This point here is the smallest, but f of c, back up over here. Whoops, let me rephrase that. This point here is a local spot where I'm smallest. So I was going down, then I'm going up. This spot down over here, because it is the smallest, if it's the smallest overall, then we call it an absolute. So this one would be an absolute minimum. Okay? This point here would be a local max. This point here would be a local min. So if I take a look, if I kind of zoom in here just to that particular area, I was going up, and then I switched to going down, so I turned. So that's got to be a local max. And then I was going down, then I started going up, so we end up with the local min. So as we take a look at just certain locations, certain areas, we have locals or relatives relative to that area. If I have the highest or the lowest, then I say I'm the absolute. So let's take a look at the graph here. Find local max and local mins from the graph of a function. Determine whether the function is increasing, decreasing, or constant. So on letter A here, where or what numbers of x does f have a local maximum? Okay, so let's see on A here. Let's see, we want to see where do we have a local max. Looks like we have a local max. Where's it the high point in a particular region? So where's it turn? When x is 1. So when x is 1, we have a maximum value. Now the actual max is 2, but in this case that's at what number x. So at what number x is that? So the local max occurs when x equals 1, and the local max, however, is 2. So we've got a little different notation here. So we might say local max at x equals 1, and the local max is 2. And that's the only spot where we're going up and then come back down. So that's going to be our only local max. Let's see our local min. Where does our local min occur? So local minimum, so if I take a look at the graph, where is it going down and then turns back up? So I get a low spot. I get a low spot here, and I get another low spot over here. So I got local mins now at x equals -1 and at x equals 3. Then if I want to identify, well, what is the local minimum value? When it was -1, my local min was 1, and I have another local min at 0. Okay, or the local min not at 0. Local min at x equals 3 is 0. Got to be careful about my language on this one. Okay, and then we take a look at letter C, and we say, all right, find the intervals on which the function is increasing and where is it decreasing. So if we take a look here at that particular spot, so where are we increasing? So our function is increasing, let's see, between these two spots and between these spots. But notice the arrow going up over there. So we are increasing between x is -1 to +1. And then again, from 3 out to infinity. Where are we decreasing? We're coming down out here from infinity, coming down out from infinity up to -1, and then from the x value of 1 to 3. So since we're coming in from negative infinity over to -1, and then again, we are going from +1 to 3. So those are the intervals where we are increasing, the intervals where we're decreasing. So kind of, again, what we're taking a look at overall is things that we can identify about a function from its graph and from its setup. So we've mentioned it before here, but on this particular graph, let's zoom back in here a little bit, do I have any one particular value that is the lowest overall? Well, yeah. I've got this point here is the lowest overall, so I would say this is an absolute minimum. No other point on the graph is lower than that point. I've got another local, okay, I've got another local minimum, but this point up here is not lower than that point. So it's not the lowest, so the absolute. If I take a look at what's the highest point on the graph, the highest point, well, on the left, I keep on going higher. On the right, I keep on going higher. So I can't end up with a singular point that ends up being the highest point on the graph. So I have no absolute max in this case. So our absolutes are the highest, the lowest. Okay. I can, however, have a local. I can have a local max because the 0.12, 2 is the highest in this particular area. So in that area, we have the highest spot. But overall, to the graph, I don't have a single value that's the largest. So what I've just explained for us here then is the definition of the absolute max and the absolute minimums. Okay? So if f is a function defined on some interval I, if there's a number u, okay, in the interval for which the value of the function at u is larger than the value of the function for any other x value for all of the x in the interval, then we have a maximum at u, and the number f evaluated at u is the absolute max. Likewise, if I have a number v, if f of v then is lower than every other f of x for every single x in the function, then we say that we have an absolute minimum. So take a look at graphs here. Find the absolute maximum, absolute minimum from the graph, and we need to take a look at some definitions here and some particular definitions. And when I say particular, particular in the sense of the fine details of the function. So if we take a look at this particular graph, do we then have let's do the absolutes, okay? Do I end up with an absolute max? Do I have any one point that is the highest of this particular graph? Okay? And on this one, I would say yes. I've got this point here. That's the highest point on the graph. So the absolute max is 6. The highest value I get to is 6. Okay? Do I have any absolute minimums? What's the lowest point I get to? So the lowest y value I get to is 1. So my absolute min is 1. Let's then take a look at the locals. Okay? So I have any local maximums. Okay? So my local maximum is in any particular region, is it the highest point? So as I'm going up and then I turn back down, 6 is indeed a local max. Now, over here at 5,5, I can't say that that is another local max because I keep coming up, but I never turn back down. So I need the neighborhood. If I'm in a neighborhood, think about it this way. If I'm living on a street, and here's one house, and here's another house, and here's another house, my rough sketching of artistic work here. If I'm the highest point in my neighborhood, then I have to have a house on my right and I have a house on my left. It is the way that we talk about the locals in that regard. So 5, this point here is not a local max. And likewise, this point here cannot be a local minimum because I don't turn back up. Now, how do we know that's the case? Because in my lost train of thought here. I was going to write down the local min. I did get a local min. The lowest value I have in a neighborhood here is 4. And so if we're the lowest in a particular region, so in this particular region, I need to be able to go back and forth over to the other side. So I have to have that turn as far as the maxes and the mins for the local. Okay. Take a look at the next graph. Let's see, do I have any absolute maximums? Okay, I do have an absolute maximum. I do end up with a high value here at 3, highest point on the graph. Do I end up with an absolute minimum? Is there one single y value that's lower than any others? In this case, I say no. It looks as though one might be, but notice this is an open dot, meaning I'm not actually including that. There's a hole in my graph. So I can get really close to that, but I can't get to it otherwise. So there's no absolute min here. Let's try to go back to color coordinating these a little bit. If I do my local max, do I have any regions where I was increasing and then decreased again? In this case, no, I do not. Do I have a local min? Do I have any values where I was going down and then turn back up? Well, I do have this. I'm going down and then I turn back up. However, that point, like I said, is open. So not only is that not a local, is that also not a absolute min, it's also not a local min in this case either. On our next graph here, if we take a look at our absolute max and our absolute min, do we have a point or a value that is higher than any other? The highest point? Yes, I've got a y value of 4. That's the highest point. Do I have a y value that's the lowest point? Actually, I get multiples in here because this whole region here is at 1. And so that whole region then kind of counts as the absolute min. So absolute min actually occurs between x equals 1 and x equals 2. But the absolute min is the y value. The absolute min is y. So let's see. Let's take a look at our local max and our local mins. So our local max, do we have any spot where we're going up and then turn back down? So I am coming up over here, but I don't turn back down. So that's not an absolute, not a local max here. Local mins, well, I'm coming down, and then on this one, I do end up turning back up. And what is that value that occurs in through here? That is 1. So in this case, I do have a local min, and my local min is 1. And taking a look at our next example, our absolute max, our absolute min. So what is the highest point on this particular graph? Well, notice the arrow there means it keeps on going. So it's going to go up to infinity and keep on going and going and going. So I end up with no absolute max here because it just keeps on going. Do I have a particular point y value that's lower than any other? And that I do. I have one here at 0. And we take a look at our local max and our local mins. So do I have any point that is going up and then back down? That would be a local max. I don't have any of those. Do I have any spots that are coming down and turning back up? I don't have any of those either. So I end up with, basically in this question, no absolute max, no local min. The only thing I have of interest in maxes and mins is I do have an absolute minimum, that one spot that goes lower than any other. In our last example, example E, let's see if I have an absolute max, absolute min. So is there one point that is higher than any other point on the graph? And it looks as though I might be able to say 4. However, that's an open dot, so I don't have that value there. So I have no absolute max. Do I have an absolute min? What's the lowest? Well, notice this line keeps on going down. That curve keeps on going down to negative infinity. So that means I have no absolute min either. As we take a look at local maxes and local mins, do I have any spot where I'm turning up and then come back down? So am I going up, turning back down? Yes, I do. I have one local max of 3. And do I have anywhere I'm going down and then turn back up for local min? I do over here. However, that again is an open dot, so that means I cannot count that. So it's not officially part of the graph. So hopefully, one of the things that you've been able to see through here is that this is just a visual inspection. Where's the biggest? Where's the lowest? That's the absolutes. And then where do I turn? Where I turn, if I'm still defined at that spot, those are then my values at which I'm looking for overall, as far as my locals. Now, we do have, if we combine these things together, we have something called the extreme value theorem. So if a function is continuous, meaning it's got no holes in it, on a closed interval from A to B. So closed intervals would be example of letter A. Okay, and let's see, another closed interval would be example C. And those are closed because their endpoints are solid, and we use those. Okay. Now, letter B is not a continuous function because I got a hole in the graph. Okay. Letter E is not a continuous function because we've got a hole in the graph. Letter, let's see here, letter D here is just not a closed function. It's not closed because it has an arrow that keeps on going. Okay. So the only ones that apply here as far as this, do we have a continuous closed interval on A to B? In our cases, we had example A and example C. Those are the only ones that qualify. Well, what are we saying? What's this theorem say then? If we have that happen, if a function is continuous and we have a closed interval, then we have an absolute maximum and an absolute minimum on that interval somewhere between A and B. So that means we tell us we have an absolute max, and we have an absolute minimum, and it's somewhere between those two values. So over here, if we take a look at those examples, where do we have an absolute max and absolute min? Well, I had them here, and I had them here, where I had both. On all of the other functions, I was missing either the max or the min, or I was missing both. So it's interesting, the extreme value theorem doesn't tell us what the extreme value is. It just tells us that the extreme value has to exist. And that's one of the interesting things about mathematics. Sometimes we end up just saying that the value is there, but we don't actually know what the value is. But since we know there is one, we can keep looking for that particular value. So as our next example shows us, on example number 6 here, or objective number 6, use a graphing utility to approximate local max and local min and to determine where a function is increasing and decreasing. So what we want to do is we want to take a look at example 6a here. And on example 6a, we have the function 6x cubed minus 12x, looking over here, plus 5, and we're going to only be between -2 and +2. So I already have this in Desmos. So in Desmos, how we denote that we're only in between some values is this piece in through here. We put it in curly braces. We say -2 to 2. So let's go ahead and graph this. Okay. So there we go, between -2 and 2. Going to have to squish that in a little bit to get all those values. So what we're taking a look at is, do we have a local maximum and a local minimum? Well, in this case, we can say we do. We're looking as far as our local min and our local max. We've got a value, what here? Let's go ahead and highlight that piece. So that's our turning point. We've got another turning point down here. So our local maximum is 11.532, and we have a local minimum of -1.532. Then if we ask, where are we increasing, where are we decreasing? We are increasing between -2 and -0.816. We're also increasing between +816 and +2. Where are we decreasing? We're decreasing then in this region in through here. We're decreasing between an x value of negative 0.816 and positive 0.816. So just by taking a look at the graph, we can start to identify all of these other parts and pieces. All right, so this video is getting a little lengthy. I'm pushing 50 minutes here. Let me go ahead and stop this video here. Let's call this part 1. We'll finish out the last probably 10-15 minutes on another video, and we'll call that part 2.